اینجا هستم در خدمت دوستان آقای دکتر صمیمی و تمام دوستان از دانشکده فنی. خب من نمیدونم آقای دکتر من شروع کنم.
بله، فقط یه معرفی مختصری هم اگر از خودتون داشته باشید ممنون میشم که دوستان با شما بیشتر آشنا بشن و بعد وارد پرزنتیشن بشید. ما خدمت شما هستیم. به قول خارجی‌ها the stage is yours.
خیلی ممنون. خب فکر میکنم معرفی رو دوستان میتونن بیوگرافی رو بخونن یه مقداری آشنا بشن. من در حال حاضر در واقع استاد دانشگاه فکر میکنم اینا هستم تو بیوگرافی. در انتها شاید بهتر بتونیم صحبت کنیم اگه دوستان سوالی داشتن. دانشگاه ویرجینیا تک هستم و فکر میکنم اول بریم سراغ پرزنتیشن و بعد در آخر هم دوستان اگه سوالی داشتن میتونم پاسخگو باشم. هم دوباره من عذرخواهی میکنم به خاطر این در واقع اختلالی که پیش اومد. خب امروز من در مورد این موضوع صحبت میخوام بکنم به خاطر اینکه زمان کمتری گرفته بشه برای من که بین ترجمه و در واقع فارسی و انگلیسی نرم. خیلی راحت تر هستم که انگلیسی براتون پرزنت بکنم. So I will talk about high voltage, high power density engineering in the era of all electric transportation and clean energy. So I start first with transportation electrification. As you can see in the left figure, you can see that transportation sector generates the largest share of greenhouse gas emission in the US. And you see that it's 29%. It includes electric cars, electric trucks, electric trains, all electric ships, and everything. This is all electric transportation. If we want to go to all electric transportation, which is the target of net zero emission by 2015 in America, we need to move towards to all electric transportation. And as I mentioned, that includes all electric vehicle, all electric trains, all electric ships, all electric aircraft. You see that I have the pictures of those on the right side of the slide. So that means that if we are moving towards all electrification, all electric transportation, that means that we will face an increase in the required power, and that's a significant increase. For example, for the more electric aircraft or all electric aircraft, this is two types of electric aircraft that we will see. So you see that for the more electric aircraft, we need only 1 megawatt of power. However, if you want to go to all electric aircraft, that means that you need to replace all the not only all the subsystems, you need to replace them by the electrically driven alternatives, but you also need to replace the thrust power fully electrically, and that means that lots of power. For here you see 20 megawatts of power you need for an all electric aircraft. This is for a wide body all electric aircraft. And we know that the total non-thrust power is about 1 megawatt. So you see, we need lots of power. That means you need to either increase the current or voltage. So if you want to go to higher voltages, because of the weight and voltage drop restriction, it is not preferred. So we go to high voltage. And there's a study, the sizing study has been done for a turboelectric aircraft. They saw that if we go from voltage 540 volt to 4.8 kilovolt, we can save 1.4 tons of cable conductor. So that means lots of saving on the weight. Another requirement when we go to all electric transportation is we need to reduce the size and weight of the apparatus. That means high power density. Okay, so now we are combining higher voltages with higher power density. That introduces a new concept, high voltage, high power density engineering. Studies, they have shown that for each kilogram, when you add to an aircraft, all electric aircraft, you add $1,000 US to the cost. And also, if you can save 1 kilogram, you can save 5,400 tons per year less carbon emission. So that's the point. We are going to all electric transportation, and we will provide a clean energy by saving on carbon emission. There is another trend that causes all those, high power density, high voltage, trends goes well. The trend is emerging wide band gap based power electronic systems that it can give you an orders of magnitude enhancement in power density and operating voltages. So in 10 years, we expect that 80% of all electric power will flow through power electronic systems. So these power electronic systems can be either part of or interact with power systems for power flow control, or interface with generation, load, and storage equipment. I have the examples of those two here on the slide. For example, for the power flow control, and you have FACS, HVDCs, SSTs. These are all the examples. And for the interfacing with grid, it's like electrified transportation, renewables, and clean energy resources, and energy storage devices. So beside power grid application that I talk, power electronics are being used and will be used in electric power system of all electric transportation. Here I have two examples, electric ship and electric aircraft. For example, development of MVDC distribution system has been targeted by US Navy for all electric ships. Another example is all electric NASA N3X aircraft that we proposed for the first time. This is an ongoing project that we have. So you see that we have, this is the system that you see is one of the architecture that we proposed for the MVDC power system of the all electric aircraft. The voltage level is 10 kilovolts DC, and you see that there are different types of power electronics here used in an all electric aircraft. So you will see this continuation of the power electronics revolution that emerges as wide band gap semiconductors. Here on the left figure, you see that the space that is associated with the silicon performance, that blue space is the space that is associated with silicon. The red line is the silicon limit, and over that dotted line shows the area that WBG systems can operate, while SI-based power electronics cannot operate. And that means higher powers and higher frequencies. This material is like SiC, gallium nitride, gallium oxide, and very soon diamond. So let's see what happens. So we know that WBG power modules, they are providing a pathway to more efficient, lighter, high temperature capable, and a smaller power converter. So you may think, okay, everything is good and everything is going well and the future is bright for WBG-based technology, but the number of failures of power electronic systems, like motors, generators, I meant power system apparatuses like motors, generators, transformers, cables, will be dramatically increased, and that may lead to brownouts or even blackouts. Why is this happening? And this is also the case for the ships electric aircraft, everything that uses WBG based power electronic system. Why is this? Is it because of the cyber attacks, or is it because of the power system requirements such as voltage or transient stabilities? No, the answer is no. It is because of accelerated aging of insulation systems under fast repetitive voltage pulses that are coming from this WBG-based power electronics. And this is expected to be one of the most significant barriers to the acceptance and utilization of WBG-based power electronics. So let's see what is exactly this. What do I mean by that? So we know that every electric component has two parts, conductors and insulators. And okay, electric machines and transformers, they have a third component that is magnetic material. When we talk about a fault in power system, that is often related to the failure of insulation of an apparatus, not other things. For example, failure of its conductor or its magnetic material. Indeed, the life of any electric equipment is determined by the life of insulation. Okay, you may say, okay, insulation has been there for a long time. So what are the problems now? Whatever problem there was there, it should have been solved by today. Okay, the answer is these problems comes because of the new and future trends that are that are emerging. And what are those trends? So the trends that I was talking about, high voltage, the need for high voltage when you are going to all electric transportation, high power density, which is combined as a new concept. And okay, I'm just working on the high voltage that you see on the right side of the slide, high voltage, high power density concept. I have high voltage. If I combine high voltage and high density, it will result in high electric field. If you combine high power and high density, it will result in high temperatures. I was talking a few slides back about emerging WBG switches in electrical conversion systems. That means high slew rates and high repetitive voltage pulses. That is a merit when you look at the wide band gap materials. However, from the insulation point of view, these two, I mean high slew rate and high repetitive voltage pulses, they pose a severe threat to the life of any insulation. Okay, now I have these three: high electric stress, high temperature, high slew rate, and high repetitive voltage pulses. If I combine those, I will have a very bad working condition for any insulation material. Okay, let's go. The case is for an aircraft or a spacecraft. That means that you are adding extreme environmental challenges like low pressure for aircraft, extreme temperatures and humidity, to the equation. You combine those together, then it will result in extremely bad working condition for any insulation material. So my focus will be on the solid dielectrics. If I want to categorize the main insulation degradation factors in solid dielectrics, I can tell there are 4: space charge, intrinsic aging, tring inception, and partial discharges. So partial discharge itself can be divided into 3 categories: surface discharge or tracking, corona discharge coming from those sharp, edges of the electrodes, or internal discharge. In the case of solid dielectrics, internal discharge has the most effect on the degradation of the solid dielectrics. And this is because of these internal discharges. They happen inside the microvoids and cavities and defects inside solid dielectrics. Can we manufacture a perfect solid dielectric with no defects or voids? It has not been achieved yet. So let's see what happens if you expose a solid dielectric to higher slew rates and higher frequencies. In the middle, I have I have a figure in the middle. I have a figure. You see that when I increase the frequency, the lifetime decreases. You see that when I decrease the slew rate, or the shorter the rise time, then the lifetime will be decreased. So although this WBG devices can lead to high power density designs, it shows that they generated voltage pulses pose a severe threat to installation system. So it is very important because the risk of the component failure can occur within hours or even minutes. I have an example that failure of an induction motor that was fed by a PWM inverter, of course, with only a frequency of 10 kilohertz, happened after 50 working hours. Here, what are the technical gaps? The technical gaps is experimental studies are limited to few kilohertz and neither in-depth explanation nor a model has been presented for the test result. And this is although that we know that we have targeted the next generation of wideband gap-based power electronics to 500 kilohertz. This is what has been targeted in the Navy. Here I have some examples. Again, I want to show you if you go to the lower pressure, we will have even worse condition. So here I have two figures. From these two figures, we can see that at low pressures, even very small microvoids can lead to PD. This is a study FEA model that we developed. So you see that I have here two electrodes, spheroid, so one HP, one grounded, and we have one air-filled void here, micrometer size, and between we have silicon gel. This is the case that you can simulate a power module. Okay, so we could see that even very small microvoids can lead to PD. PDs are longer in duration. You see that mean PD duration increases with the pressure decreases, and also you see that more intense PDs, which you can see in the in terms of PD, I mean mean through charge. You can see mean through charge increases as you decrease the pressure. What are the technical gaps? As I said, it's limited to few. The studies is limited to few kilohertz and few tens of kV per microsecond, which is the state of art for the SI-based power electronics. So here we are trying to understand what happens on a few kilohertz and few hundreds of kV per microseconds. And by that means we want to understand what are the effects on the different types of insulation degradation and what are the effects on the various types of insulation materials and systems that are used in various power system components. The first component that we study is the power module itself. The power module creates all those problems for us, but itself is being exposed to that aging. So what we are doing here, we're doing some experimental investigation, modeling and simulation, and also search for novel dielectrics and installation systems. This is where the transformative ideas are there. So we worked on nonlinear field dependent conductivity materials in this area and high temperature dielectric liquids instead of silicon gel. It is very important subject since SIGRE working group and has recently been formed. This is this D147. There are there are three subgroups there: rotating machine, transformers, and electronics. I'm the chair of electronics, where we study the accelerated insulation aging in WBG-based power modules and converters. Okay, what do we do for the power? Let's go to power modules. I have here an example. The highest breakdown voltage capability, what we call it blocking voltage, for SI IGBT is 6.5 kV. This is for a commercial SI IGBT. However, for when you go to SiC IGBT, it's been reported that the highest voltage is 15 kilovolt for 80 amperes or 24 kilovolt for 30 amperes. So you see that the blocking voltage is here 2.3 times higher than SI IGBT. And you see, you don't see here, but I can tell you that the volume is 1/3 of that for SI IGBT. That translates into higher electric fields, and also you have power modules, which are SIC, that means exposing to higher slew rates, pulses. That means extremely poor environment for installation system. So there are some work that here we did here. So I have here on the left, I have the schematic of an IGBT diode substrate. So you see here, and the metallized ceramic substrate you see here is well known and is an established installation technology that we use for power module packaging. Because of the high electric fields, especially at the edges of the copper metallization, there are partial discharges that can be initiated from this region. So the situation even gets worse because of the extremely sharp edges that we have for the brazing below the metallization. So there are some work that has been done to reduce the electric field in different parts of the module, and those are using different geometrical techniques like metal layer offset, protruding substrate, or a stacked substrate design. So either individually or combined. But none of them can solve the high electric field issue inside this high power density power module. So we could use, we could show that the use of the combination of these geometrical techniques and also applying a nonlinear FDC layer can solve the problem of high electric field inside the modules to voltages up to 30 kilovolts. So this is the work that we have done, and you can find the details in our paper. Another trend, if you remember, I was talking about high power density modules. When you talk about high power means that high temperature. Okay. I have some questions. Are semiconductors okay with these high temperatures? The answer is yes. This WBG semiconductor materials like SiC, GaN, they are enabled to be operated over 500 Celsius degrees. Okay, another question. Are packaging materials okay with these high temperatures? Well, ceramic substrate can be operated up to 600 Celsius degrees, no problem. However, the operating range of the temperature for the silicone gel is limited to 200 Celsius degrees, and for the continuous use is even lower than that, is 175 Celsius degrees. So here you see, again, problem is insulation. What can we do other than only managing this high temperatures by some using some cooling methods? So the transformative idea here is using high temperature dielectric liquids. I have an example. For example, there is an industrial liquid that was primarily intended to use for heat transfer of 350 degrees Celsius. It has high thermal stability, low toxicity, and it is also a very great dielectric liquid. So that's one of the transformative ideas that you can replace with the silicone gel to have the answer. However, it has some challenges. For example, as you go to higher temperature, the dielectric strength tends to be lower. What can we do? Are there any answers for that? Yes, there are some challenges, but there are some solutions for those that we can work on that, and we are working on those. So let's go to another aspect of high voltage, high power density engineering, and that's emerging unconventional power systems. Why do I call this unconventional power system? Because in conventional power system or power grids that we know, three things are fixed, okay? And then one is the type of the voltage, which is AC, we have DC, but it's only point to point. The frequency is 50 or 60 hertz, and the voltage level. Each country has its own voltage level standard. This is for US. So these are all These are all predetermined or fixed. However, when you go to unconventional power systems, and by those I mean like all electric aircraft, all electric ships, these three parameters, they can be variable. And also you bring into equation the weight, the volume, so you can find all those three parameters through optimization in a way to maximize your power density. So here I want to talk about a project that we are working on that, and it's high power density, cost-effective MVDC aircraft cable. So here our goal is to develop a power dense, cost-effective 10 kV DC and 1 kiloampere cable for a twin aisle all electric aircraft. And what are the state of the art? The state of the art, the existing voltage, the highest voltage levels that are existing now on the aircraft is 230 volt AC or 270 minus plus and minus DC, which is for the Boeing 787. And now we are designing cable for 10 kilovolt DC. Why this high power? And we are going, as you can see, the total electric power demand now for a Boeing 787 is 1 megawatt ampere. Now we are going to 25 megawatt. Why this high power? Because it is the power that needs an aircraft needs for takeoff. And this is the propulsive power that you need for the takeoff, and it's 25 megawatts. So here I have a turboelectric NASA Entry X aircraft. That's a wide body aircraft. It is not an all electric. It is a turboelectric aircraft. So because the generation there is non-electric, they have two turbo engines, each of them 25 megawatts on each wing, because this has been seen because of the single, if you have a single engine fail scenario, so you need to have to provide that 20 megawatts power. So here what we did, we took this N3X aircraft and we turned that to an all electric aircraft. And so, So for that, here you see the architecture of the power electronics, power system that we have on an all electric aircraft. We did the design in a way that is reliable in the terms of the failures. We did study that for both normal and single contingencies, and this is the one that that leads to the lower cost. Here we have published some papers. You can see the details, for example, on the IEEE transaction on transportation and electrification for the architecture of the all-electric aircraft that we did that for the first time. So the main part of this project is about designing a medium voltage cable, DC cable for all electric aircraft. On the left, I have a conventional medium voltage DC cable for terrestrial application, and we are trying to turn that to a cable for all electric aircraft. There are some differences. The main difference and the the novelty of the project is on the installation of the cable. Of course, we will change the core conductor to an AAC-TW, which is a lightweight conductor. Our first target is aluminum. However, the main goal is changing the insulation. And that means that we are taking only this. You see that for the terrestrial cable, we have only one layer of insulation. Here, what we are doing, we're proposing to have multifunctional, multi-layer electric insulation. So we could see that, we could show that for the same voltage breakdown, a multifunctional, multi-layer electric insulation can result in around 50% reduction in insulation thickness. That means reduction in the weight of the insulation. So what are other things here? The most important things here is that the heat transfer to the ambient. So heat transfer to the ambient here, because of the lower pressure due to convection, it's going to be very limited. So beside electrical challenges that we face here another big challenge, that is transferring heat because of Joule heating in the core conductor to the low pressure ambient. So here we are working on this problem, which is a complex multi-physics problem, and we are using computational fluid dynamics, heat transfer in solids, and electric field and current together to model development and simulations. So now after we could couple this multi-physics model that we developed, then we will design the optimal cable for our all-electric aircraft. This is a very complex multi-objective problems where there are so many variables that we are taking into account. For example, the type of the material, the thickness of the dielectric layers, the maximum dielectric breakdown voltage of each layer and the whole layer, the maximum ampacity, the maximum, the minimum overall thickness of the system, the minimum overall weight of the system. So that's a very interesting project. So it can be extended to all other electric equipment. Here you see on the right, I have a figure. I have a figure that you see the historical reduction of a stator ground wall thickness. So you see that it starts from year 1911 to year 2005. I didn't have the figure to show the upcoming years, but this trend has been continued. So you see that blue is insulation. That blue is the stator ground wall. So you see that is reducing from 15 millimeter to 0.5 millimeter. It's a very dramatic reduction. So you see that. However, the power is the same, the voltage is the same. So you see that the power is the same because of the amount of the copper that you see. It's the same. So whatever happens when we are going to high density, design, it happens to the insulation, okay, not the conductor. So insulation plays a very important role in our future of transportation, electrification. Okay, I will take you to the sea, and I will take you to the ship. So peak load in a modern naval ship, it may reach to 100 megawatts. It's a huge amount of power. For example, for Navy ships, MVDC at the voltage level of 12 to 18 kilovolt is preferred, which is leading to both more weight reduction and also losses. So here I have you can see a figure of a naval ship. Here I want to look at the problem from another perspective. And So as I explained, that the Achilles heels of the high voltage, high power density engineering is the compact and reliable design of installation systems, especially under harsh environment conditions. For example, for the ship, what are those harsh environment conditions? Is the salt pollution and it's the humidity. So the safety of the sailors and safety of the missions is very important. That's why we need to look at the health of the installation in all electric transportation. And here in particular, I'm talking about all electric ship. So we know that the production of perfect installation materials with no defect has not been yet achieved. So what can we do? We can monitor the health of installation. How we can do that? By monitoring the partial discharge signals that are coming from those defects. We know that we do the PD test as a routine factory test to ensure the acceptable quality of our installation system. However, over time, that initially accepted quality will be gradually deteriorated. So, and that's because of the partial discharges. That's because of the electrical stresses. That's because of the thermal stresses. That's because of the mechanical stresses. So then you can also add environmental impact. So we can consider PD as an indicator of the health of any installation system. For example, here I will talk about the Navy. So what happens? What do we want to do here? We want to intelligently monitor and assess the health of electrical installation in all electric transportation. We want to do that online because then you don't have to shut down your system to do the tests. So, and what do we want to do? We want to we want to detect, recognize, and localize the PDs. How do we do that? How do we detect those? So for those now commercially available systems, they cannot detect PDs more than few kilohertz. So here, first you need to innovate some antennas and receivers to detect those, especially for this new trends that are coming with WBG-based power electronic systems. So, and then you need to recognize and localize the PDs because we have lots of electric equipment like energy storage, cables, transformers in the power corridor of, for example, a Navy ship or other, electric transportation systems. That's a very complex environment which you face large amount of PD sources as input. You have mixture of all those PD sources. What do you need to do? You need to separate and recognize multiple PD sources. For example, for even one cable and even one type of PD, you will have lots of inputs. So what do we do here? We are using AI, artificial intelligence and machine learning techniques as a promising technique to separate the signals. For example, we use deep learning techniques to separate PD signals of the corona discharge type from multiple sources that we had for different electrode geometries that I have the papers here. And it was different geometries, for example, needle to needle, sphere to sphere, plate to plate. So we did those both under atmospheric pressure and low pressure, and we could show that it is highly reliable. We can use this technique. And I have the figure here. This is for one of our test setups, and you can find the details in the papers that I've mentioned here. Yeah, you can find the details there. So now let me take you to the space. What are the problems there regarding high voltage, high power density engineering? Again, key is the insulation. The key issue is the insulation. Here I have some figures that are coming from a study of spacecraft anomalies. They did a study on their power system and on their anomalies, and they could show that they could find that 3/4 of the failures were coming from electrical, which were related to their power system. And here on the left, the bottom figure, you see that the half of those problems are related to the solar arrays, and it is all related to insolation. And on the middle, I have a figure. You can see that 45% of the failures result in a loss of mission. 80% of the fault significantly affects the spacecraft mission. And on the right, I have a very interesting fact that the time to the failure of this spacecraft on 50% happens during the first year of their operation. So what happens? What's the problem here? So the operating environment for this high altitude spacecraft, it contains lots of space plasma, energetic particle radiation. They will face extreme temperature. They will face cosmic rays. So these energetic electrons, they can penetrate to the aluminum shielding layer of the spacecraft, and they can deposit in insulation materials, which will cause what we call electrostatic discharges between different parts of the spacecraft, and it will cause electromagnetic disturbances and possible damage, and it will cause degradation of the spacecraft electronics that we use there, and also spacecraft anomalies. So this is a very interesting subject. Why is it so important? Because hundreds of military, government, and commercial satellites nowadays, they reside in GEO. That is geosynchronous Earth orbit, okay? And that is 22,000 miles away from us. So it's very good to provide communication, meteorology, and national security services. However, it's very far from maintenance. So it's very important for us to have reliable high altitude spacecraft or satellites. That's where it's a vital need to address those insulation issues, such as deep dielectric charging that I talked in the previous slide. So here is, there is very interesting trend now, which is very interesting, and that's the use of the space solar power stations. It is a very new clean energy that is the future of the clean energy. And these space solar power stations, they have so many advantages. They provide power 24 hours a day. It is not like, solar panels that we have. It is only during the sunlight. So the solar irradiance in a space is 40% stronger than the ground. And the power, of course, can be directed to different locations as you demand. And this SSPS, they eliminate the need for power lines. That means it is less vulnerable to terrestrial natural disaster. And we know that solar energy is not affected by the fluctuations in energy prices like fossil fuels. So what happens? What are the target power for this SSPS? So the target power, it is very interesting that I let you know that it's the range of megawatt or even gigawatt. And China, US, Japan, they are the countries that are actively working on this subject. We know that the largest human-made satellite is the International Space Station. It only generates 100 kilowatts of the power at the voltage range of 160 and delivers at the voltage of 120. So when we are targeting megawatt, we need to move toward higher voltages. Here, when I talk about higher voltage, it is relatively to that 120 volt, okay? Keep that in mind. So 500 volt here is considered high voltage for a space application. So for such a huge amount of power, we will need ultra large spacecraft. That means weight will be the most significant barrier. And again, what happens? We need to reduce the shield thickness of the different part of SSPS. That will lead to severe deep dielectric charging. So these are all challenges and that we'll face when we want to, for example, design a spacecraft. And the key here again is installation. Let me take you to the moon, okay? And we know that the demand for lunar space power, it is dramatically increasing to the megawatt level, and it's because of the number of the public and private entities setting their sight toward a future on the moon. And for example, here, NASA's goal is to sustain human presence of more than 100 personnel on the moon. So that means we need power lines of different lengths and power transfer capabilities to form a lunar-based power system to connect different types and sizes of this power generation, storage, and loads in different locations on moons. It's very interesting. So here, what are the challenges? What are the challenges when you go to the moon and you want to build a power system? The challenge is extreme lunar environment. Very interesting. The moon is almost vacuum. So when I say vacuum, means that there is no convection above the surface of the moon. That means when you are transmitting power through transmission line, the only method that you can transfer the joule heating from the conductors is through radiation, which is not an effective method. Okay, there is another thing, and that's the poor thermal conductivity of the lunar soil. That is a problem when you want to bury the transmission line into the ground of the moon. Of course, I should say that the lunar soil is a very good dielectric also. They have been they've done some research on that. So here, the biggest issue on the moon is dissipating the power loss of the transmission line. So to do this, we need to minimize the power loss by using DC type instead of, for example, AC, and also moving again to higher voltages. There are other extreme environments on the moon, like which is the same for the space, and those are the cosmic rays, UV radiation, extreme temperatures. I should say this extreme temperatures goes from minus 20 Celsius degrees at night to 110 degrees Celsius on the at noon. So it's a very challenging problem if you want to, for example, design a power cable, DC power cable on the moon. This is my last slide, which I will talk about again, power grid. So there is one Princeton Net Zero America report that we always refer to that when we want to work to achieve a net zero emission, for example, in America by 2015. It says that high voltage transmission capacity must expand 60% in 10 years and triple by in 30 years. So that is needed to connect further wind and solar solar facilities that we have to the loads. And this expansion requires a capital investment. Here I have billions of dollars in 10 years and then trillions of dollars by 30 years. Okay, what are the barriers here? The barrier here is that the owners of transmission grid, they have mainly focused now on increasing the profits through increasing the use of their current assets rather than investing in new assets, because it takes a lot of time, a long period to be commissioned, and it has a low return. Another barrier is the environmental and legal requirements for taking the right of way, which is a long time, and also the legal costs that are exceeding from the construction of the line. So is there any solution for this? Yes, the answer is yes. The solution is through the design of novel, cost-effective, restructured, high-power density overhead lines that I have proposed, and it's been recently funded by NSF. So here I showed in my recent papers that here I have some of them, and you can see I showed that it is possible to increase significantly the power transfer capability of the overhead lines, and at the same time you can reduce its dimension. So again, that's high voltage, high power density engineering concept. So here, for example, on the right figure, I have a conventional 500 kV line. And I have one restructured design that is for 8 subconductors. And because I wanted to achieve the same cost, I kept the total minimum cross-section of the restructured line less than that of the conventional line. So the restructured line, I could show that I can get to the power delivery of 1.43 times over that conventional type. And also I could show that I can decrease the tower width 2.53 times. That if you combine those, it leads to a power density of 3.6 lower over than that conventional line. So this has been achieved by optimal determining of the number, size, and location of all those subconductors. By that, I finish my presentation, and thank you for attending and listening to this, to my presentation. And if you have any questions, I am here to answer those.
خیلی ممنون خانم دکتر. من سویچ کنم به فارسی.
بله بله.
البته اکو صدای خودم هم میشنوم، نمیدونم که چرا غیر از من و شما. من با اجازه شما چون میوت میکنم، موقع پاسخ دادن بی زحمت مجددا فعالش بکنید. خیلی ارائه جذابی بود لااقل برای من که تقریبا همه جا ما رو بردید، از دریا و هوا و زمین و آسمان و ما، و احتمالا شما یکی از افرادی خواهید بود که اون ویژنی که ما از فیلم های ساینس فیکشن داریم در محقق کردنش میکوشید. من یکی دو تا سوال دارم، ولی اجازه بدید که چون من خودم بالاخره یه خورده فشار قوی طورم، دوستانی که حاضر هستن اگر سوالی دارن میتونن تو قسمت چت بنویسن یا دستشون رو بلند بکنن، میکروفونشون رو روشن بکنن و سوالات رو بپرسن. اینم بگم که یه تعداد زیادی از دوستان تلاش کردن که جوین بشن به این جلسه، ولی هم مشکلی که شما داشتید خانم دکتر دارن بقیه هم برخورده بودن که اون دکمه جوین کانورسیشن فعال نبوده. حالا ما این ویدیو رو در اختیارشون خواهیم گذاشت. شاید سوالاتی اگر دوستان داشتن میتونن با خودم دکتر در تماس باشن از طریق ایمیل. دوستان اگر سوالی دارن ممنون میشم که دستشون رو بلند بکنن یا تایپ بکنن. و این سوالات رو مطرح بکنم. آقای دکتر ایمانینی خدمت شما هستیم.
خب عرض سلام و خسته نباشید خدمت خانم دکتر قاسمی و همینطور سایر حضار محترم. خیلی متشکرم خانم دکتر، ارائه بسیار خوب و موضوعاتی بودش که برای خود من خیلی جالب بود و اتفاقا حالا ما هم به عنوان متخصص الکترونیک قدرت چون به سمت کار کردن توی شبکه‌های مدیوم ولتاژ داریم میریم، واقعا این چالش رو داریم میبینیم که برای طراحی‌هایی که میخوایم برای ترانسفورماتورامون انجام بدیم، ترانسفورماتورهای های فریکونسی، یکی از مسائلی که وجود داره، حالا یه وجهش رو در حقیقت شما اینجا روشن کردید، ولی طراحی‌ها در واقع باید مجدد انجام بشه و چالش‌های جدیدی که باهاش داریم مواجه میشیم. من یه سوالی در ارتباط با بحث هواپیمای الکتریکی که به نظر رسید، حالا طراحیش رو، اون طراحی در واقع طراحی که در اینجا راجبش صحبت شد رو، من استنباطم این بود که تیم شما و در واقع جناب عالی انجام دادید به این صورت که یک شبکه 10 کیلوولت رو در نظر گرفتید، بعد خب یه طراحی دادید برای این سیستم، ضمن اینکه گفتید خب باید کابلایی هم بتونه تو این شرایط در واقع کار بکنه و روی اون هم یه صحبتی شد. منتها صحبت من راجع به البته نمیدونم، شاید اصلا شما به این موضوع نمیدونم ورود شاید نکرده باشید، نیازی هم نبوده باشه ورود بکنید. منتها من از دید کسی که طراح یه سیستم الکترونیک قدرت هست دارم به این فکر میکنم که اگر ما 10 کیلوولت رو داشته باشیم، خب این رو چگونه باید کاهشش بدیم و مبدل هامون رو برای چه سطح ولتاژی در واقع دیزاین میکنیم. منظورم اینه که اول یک کاهش ولتاژ داشته باشیم، همون مبدلای سابق رو استفاده بکنیم، یا اینکه نه مبدلی داشته باشیم که در ورودیش 10 کیلوولته، بعد از اون طرف با استفاده از ترانسفورماتور های فریکونسی که توش دیزاین میکنیم ولتاژ رو بیاریم پایین. این برای من سوالی شد، گفتم از شما سوال بکنم. خیلی ممنون میشم اگر نظرتون رو بفرمایید. خیلی ممنون.
خانم دکتر فقط میکروفونتون هم روشن کنید.
بله من فکر کردم نمیتونستم روشن بکنم. ما اینجا مبدل ها رو مدل نکردیم، 14 تا موتور در نظر گرفتیم. در واقع این 14 تا موتور از کجا در نظر گرفتیم؟ این مال در واقع طراحی یه هواپیمای میشه گفت مور الکتریک ایرکرافت ناسا، تربو الکتریک ایرکرافت، که اینی که اینا در نظر گرفتن تو این تربو الکتریک، خب تربو انجینه، از طریق تربو انجین میاد. ما اینجا کاری که کردیم، اومدیم در واقع این تربو انجین رو که 50 مگاوات پاور رو باید تامین میکرد، 25 مگاوات لازمه برای تیک آف. دو تا تربو انجین 25 مگاوات روی هر بال هواپیما گذاشتن که اگر که فیل کرد این بتونه بیاد در واقع کل بار هواپیما رو بتونه در واقع تامین بکنه. اون کاری که ما کردیم این بود که ما این تربو انجین رو با باتری، با فیول سل، با سوپر کپاسیتر جایگزین کردیم، الکتروکمیکال انرژی یونیت ها در واقع جایگزین کردیم و گفتیم که این سیستم باشه all electric aircraft. بعد اینا 14 تا موتور خب داشتن برای پروپالشن. ما هم همون قاعدتاً به موتورها دست نزدیم، همون 14 تا موتور اونا رو استفاده کردیم، 14 تا یعنی 7 تا سمت راست، 7 تا سمت چپ، و وارد طراحی مبدل ها یا موتورها ما نشدیم. ما فقط این کامپوننت ها رو گذاشتیم کنار هم، به دید سیستمی نگاه کردیم، گفتیم که اگر که این سیستم رو داشته باشیم چرا اصلا ما رفتیم این آرکیتکچر رو طراحی بکنیم؟ به خاطر اینکه وقتی می‌خواستیم کابلی رو که پیشنهاد داده بودیم طراحی بکنیم در سطح 10 کیلوولت که مثبت و منفی 5 کیلوولت هست، خب ما ولتاژ رو میدونستیم چقدره اما توان رو نمیدونستیم. به خاطر اینکه بدونیم خب اگر که هواپیمای الکتریک ایرکرافت که حالا ما داریم صحبتش هم میکنیم بسیار دور هست تا ما برسیم بهش، مثلا همین هواپیمای تربو الکتریک که برای ناسا پاسیبل فلایت تایمش 20 سال دیگه است، یعنی این که بخوان اولین پروازش 20 سال دیگه است. حالا این خود این خیلی یه چیزیه که برای خیلی آینده است. این ولتاژ رو ما تعیین نکرده بودیم، این توسط کارفرما تعیین شده بود که می‌خواستن 10 کیلوولت باشه. حالا ما می‌خواستیم خب جریان عبوری کابل چقدره، برای اینکه یه در واقع دیدی داشته باشیم خب می‌خوایم کابلی که طراحی کنیم چقدر جریان قراره ازش به صورت واقعی رد بشه. این بود که اومدیم این آرکیتکچرها رو طراحی کردیم، اومدیم در نظر گرفتیم هم نورمال هم سینگل کانتینجنسی، همین که اگر که در واقع کلیدها فیل بکنن، همه اینا رو در نظر گرفتیم. 3 تا توی این دقیقاً علاقمند باشین توی پیپر ترانسپورتیشن الکتریفیکیشن ما هست، 3 تا آرکیتکچر ما پروپوز کردیم که اینها بهترین هستن به لحاظ ریلایبیلیتی و به لحاظ کاست تا پیدا بکنیم جریان کابل رو بخوایم پیدا بکنیم. هدف اصلی ما طراحی خود کابله، نه طراحی در واقع هیچ کدوم از اون ساب سیستم‌های دیگه.
بله خانم دکتر خیلی متشکرم. منم حدس زدم که همین موضوع هست، منتها در واقع از این جهت این رو بگم که حالا فکری شده یا نه، چون بعد از کابل چون استفاده اون ولتاژ توسط مبدلا باید انجام بشه، به نظر میرسه یه پیچیدگی زیادی خواهد داشت، ولی طبیعتا این کار احتمالاً حالا بیشتر با دید الکترونیک قدرتی شاید باید حل بشه. خیلی ممنونم از تو.
نه خواهش میکنم. البته طراحی در واقع مبدل‌ها در فشار کم که خب برای هواپیما و مالا اسپیس کرافت همین میشه، خودش موضوع روز هستش.
متشکرم، ممنونم از توضیحات.
سلامت باشی.
خب توی قسمت چت هم یکی از دوستان یه سوال پرسید، حالا اگر تا بقیه دوستانم سوالاتشون پرسن، گفتن این که تنش گرانشی و فشار هوا بسته به ایرکرافت و ارتفاع پروازی یا مانورش چقدر توی طراحی یا پیری عایق‌هامون تاثیر داره؟
خب فشار کم که خیلی تاثیر داره، همونطوری که من نشون دادم توی یکی از اسلایدا که در واقع ما داریم روش هم کار میکنیم. PD خب میره بالا، اینتنسیتیش میره بالا. در واقع توی فشار کم که من دارم الان البته صحبت میکنم، فشار 1/5 فشار در واقع سطح زمین رو ما در نظر گرفتیم. ارتفاعی که هواپیما پرواز میکنه هولوش 12 کیلومتر و در واقع فشار هوام 19 کیلو پاسکال تقریبا که میشه 1/5 فشار هوا. این خیلی خیلی تأثیر داره روی در واقع پیری عایق و اونم به خاطر اینه که PD افزایش پیدا میکنه، هم در واقع زمانی که PD mean duration تایمش زیاد میشه، هم خود اون ترو چارجش زیاد میشه که در واقع نشون میده اینتنسیتی PD بالا میره. این اثر ارتفاع هستش که بله خیلی تأثیر داره روی پیری عایق.
بسیار عالی، ممنون.
البته خب این عایق شامل تمام چیزا هست دیگه، مبدلا هست، کابل هست، ژنراتور هست، در واقع موتور هست، همه اینا هر جایی که عایق دارین توش تاثیر داره.
خیلی عالی، ممنون از پاسختون. یه سوال، حالا اگر دوستان با سوالی دارن، یکی دیگه از دوستانم دستشون بلند کردن فکر میکنم، البته دکتر که سوال رو پرسیدن، ببینم مسائل دوستان اگر کسی هستن. خب حالا یه سوالا من برام جالبه بیشتر از لحاظ دید آکادمیک. کاری که شما انجام میدید طبیعتاً به حالا مقدار زیادی بگیم شیمی و دانش مواد احتیاج داره، خصوصاً سنتز این عایق‌ها. یکی میخوام بدونم که آیا این کارها به اصطلاح در انستیتوت شما انجام میشه یا پارتنری در بخش دیگری از دانشکده یا دانشگاه‌های دیگه این کار انجام میده؟ و سوال دوم اینه که برای این بحث پیدی در فشار کم فکر میکنم بایستی از دید اکسپریمنتال و آزمایشگاهی فشار کم ایجاد بشه. خواستم بپرسم که آیا شما این سیستم های وکیوم اینا رو، یعنی کابلایی که میسازی رو در وکیوم تست میکنید یا اینکه صرفا پروپوز کردید روشی که بشه پی دی ها رو از هم جدا کرد، سپریت کرد و این حالا اونجا هم کار خواهد کرد؟ این دوتا هم اگر پاسخ بدید ممنون میشم.
خب من این یعنی سوال آخری رو اول بگم. بله، ما تجهیزاتش رو داریم، محفظه فشار کم داریم. در حال حاضر ما هنوز به مرحله تست کابل نرسیدیم، ولی این کار رو خواهیم کرد. کابل رو قراره بسازیم در واقع در مراحل بعدی. بعد تمام اونا رو هم که گفتم در مورد پیدی، در واقع قابلیت تستش رو داریم. این مسئله تستش بود. بعد سوال اول شما این بود که ما خودمون هیچ ماده جدیدی طراحی نمی کنیم آقای دکتر. ماده جدیدی طراحی نمی کنیم، از موادی که هست و به صورت تجاری موجود هست توی در واقع این طراحی کیبلمون استفاده میکنیم. البته با چند تا کامپنی و مشارکت داریم، ولی بازم فقط برای گرفتن مواد هست. خب این مواد رو مثلا برای همین کابل این هستش که شما با چه ضخامتی استفاده بکنین، خیلی مهمه. مثلا همون که کابل که گفتم چند لایه میکنین، این که اون لایه ها رو کیو اول بذاریم، کیو دوم، کیو سوم، خیلی مهمه. یعنی چه نوبتی مثلا ما بذاریم. اینا یه سری الکتریک فیلمایی هستن که ما میگیریم و تو اون مرحله‌ای که بخوایم در واقع بسازیم اون تستا رو روش انجام میدیم.
خیلی عالی. یه سوال در مورد همین ساختار کابل هم بپرسم. خب این کابلای چند لایه به اصطلاح که به اصطلاح الکتریک فیلد دیسپلیسمنت رو احتمالاً رقم میزنه، توی کابل های معمولی که امروز استفاده میشن که تیپیکال XLP هستن خب به کار نمیره. خواستم ببینم غیر از این اپلیکیشنی که شما دنبال میکنید، آیا این مثلا ساختار مالتی لیری که از لایه‌های مختلف استفاده بشه در سیستم های کابلی دیگری هم در حال حاضر استفاده میشه یا خیر؟
نه این جای دیگه در حال حاضر استفاده نمیشه، ولی میتونه استفاده بشه.
آره، این برای خود من خیلی جذابه، چون یک کابلای خیلی خیلی قدیمی هستن که چند لایه بودن ولی بعد XLP اومد و به خاطر قدرتش همه رو کنار زد. الان خب این طراحی جذاب و جدیدیه که حالا برای اون اپلیکیشنه، ولی احتمالاً میتونه در جای دیگه هم کاربرد داشته باشه. خیلی ممنون از
آخای ببخشید من نمیخواستم.
خواهش میکنم. نه خواستم تشکر بکنم از پاسختون.
میتونه مثلا برای افزایش جریان عبوری کابل HVDC مثلا میتونه استفاده بشه. البته منظورم آندرگراونده.
بله. خیلی عالی، ممنون از پاسختون. سایر دوستان حاضر باز اگر سوالی دارید مطرح بفرمایید. یک سوال دیگه اگر باشه شاید پاسخ بدن خانم دکتر و بعد میتونیم سشن رو ببندیم. دوستان اگر دستشون رو بلند کنن یا سوال رو در قسمت چت بپرسن. آقای دکتر حمزه دارن تایپ میکنن تا بنویسن. من باز مجددا تشکر میکنم. میدونم سرتون خیلی 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 شلوغه به معنای واقعی کلمه و من از طرف همگی دوستانی که چه الان حاضر هستن چه بعداً ویدیو رو میبینن خواستم تشکر مخصوص بکنم از وقتی که اختصاص دارید برای این ارائه جذاب. و اگر به نحوی بشه اون فایل ارائهتون حالا حجمشو کم کرد، PDF کرد، برای ما بفرستید که در اختیار دوستان بگذاریم، این هم حالا خیلی خوب خواهد بود در کنار این ویدیو پریزنتیشن.
خیلی ممنون. من هم میخواستم خیلی تشکر بکنم. من خیلی الان خوشحال هستم، باعث افتخار من هست که برای بچه‌های دانشکده فنی در مورد مهندسی قدرت صحبت کردم. امیدوارم که بچه‌ها خوششون اومده باشه و تونسته باشم و امیدوارم تونسته باشم یه بخشایی از کاری رو که در مهندسی قدرت میشه انجام داد در آینده اون رو نشون بدم و امیدوارم تونسته باشم علاقه ای رو ایجاد کنم، بچه ها خوششون اومده باشه. و
حتما همینطور خانم دکتر، اینقدر ارائهتون جذاب بود که من فکر میکنم که همگی دوستان اون حسی که لااقل من الان دارم رو تا حدودی دارن. من خیلی ممنونم از شما. بیش از این وقت شما رو نمیگیرم و براتون آرزوی موفقیت و سلامتی و به اصطلاح جوایز متعدد و موفقیت‌های روزافزون در آینده نزدیک دارم. ممنون از ارائه‌ای که داشتید و حضورتون. من از طرف همگی دوستان حاضر از شما خداحافظی میکنم.
سلامت باشین. من هم خیلی خوشحال شدم که اینجا بودم در کنار شما دوستان و عزیزان. امیدوارم که همگی سلامت باشید و موفق باشید و شاد باشید.
ممنون خانم دکتر. روزتون بخیر باشه.
شب شما هم اونجا بخیر باشه. خدا هم نگهدارتون باشه.
خدا نگهدارم.
خدا حافظ.